Hello, I'm Blake Blueheart. Today I'm going to be talking to you about an exoplanet, KOI 55b, a rocky world hotter than the sun. So just some background information on KOI 55b. It is commonly called Kepler 70b, which I'll be referring to it for the rest of this project. It has an orbital period of 5.76 hours. It has a mass of almost half of that of the Earth, which equates to 2.63 times 10 to the 24th kilograms. It has a radius of 0.76 of the Earth, which equates to 4.99 times 10 to the 6 meters, and it orbits a subdwarf star called KOI 55. This is commonly called Kepler 70. This has a mass of half of that of our Sun, which is roughly 9.95 times 10 to the 29th kilograms, and it has a radius of 0.2 of our Sun, which is 6.96 times 10 to the 8th meters. Let's go over a quick history of its sun, Kepler 70. Kepler 70 was a main sequence star millions of years ago. That means it used to be a star like our own sun. But then it went through its red giant stage about 18.4 million years ago. This is the death stage of a star, where it swells up beyond its original size, and it engulfed both of its orbiting gas giants, Kepler 70b and Kepler 70c, and resulting in a subdwarf Kepler 70 star at 27,730 Kelvin, about 50,000 degrees Fahrenheit. What's magnificent about this red giant stage is that it didn't completely destroy its orbiting planets, but actually resulted in two new planets that were much smaller than their original form. We'll talk about it here in the results for Kepler 70b. As stated before, the red giant phase stripped the planet of any atmosphere and left only a hot planetary core, and transformed the gas giant to a terrestrial planet, meaning it's just a rocky planet composed of mainly silicate rocks and metals. Its surface is observed to be at 7,300 Kelvin, roughly 1,300 Kelvin hotter than the surface of the Sun, and is the hottest exoplanet as of 2017. It's so hot, in fact, the planet is slowly evaporating. Let's talk about the discovery of Kepler 70b. It was first observed in 2011 by NASA's Kepler telescope, using the transit method, where it observed changes in the brightness of the central star during which the planet is passing by the star. From this method, it results directly in the exoplanet's radius and the period of orbit. These are both calculated from the dip shown in the curve on the left. Let's further dive into the properties of the Kepler 70 system. As seen on the right, the mass of the central star can be directly calculated from the observed brightness in the transit experiment. The mass of the exoplanet can also be found from the transit method. As each exoplanet slightly accelerates or wobbles in the time between its transits, it allows for a calculation for mass based on this acceleration value. Once we've observed the necessary values from the transit experiment for Kepler 70b, we can also calculate multiple other values, such as the orbital radius. To do this, set the universal law of gravitation, shown here, equal to a Newton's second law for radial acceleration, shown here. In doing this, your masses will cancel out and you'll end up with an expression for v squared, the universal gravitation constant times the mass of the central sun over the orbital radius. From there, we can figure, since velocity equals displacement over time, displacement equals the circumference of the orbit, or 2 pi, times the orbital radius, over t, or the period of orbit. Upon substituting this new expression for v and setting equal to the expression for v squared we derived earlier, we can configure a new value for the orbital radius, the cube root of period squared times the universal constant of gravitation times the mass of the central sun over 4 pi squared. Now, upon substituting the values we found out earlier from our experiments, we found out the orbital radius equals 8.98 times 10 to the 8th meters. To figure the orbital velocity, set the force of gravity equals the mass times the radial acceleration. Substituting for radial acceleration as v squared over r, and substituting for the force of gravity as the universal law of gravitation, we can figure that v squared equals universal law of gravitation times the mass of the sun over the orbital radius. Upon solving for v, we get v equals the square root of the universal constant for gravitation times the mass of the central sun over the orbital radius. When substituting the values we found earlier from the transit experiment, we get the velocity of the exoplanet equals 271,918 meters per second, much larger than the velocity of the Earth, which is a mere 30,000 meters per second. Finally, one can calculate the gravitational field strength of this exoplanet. And setting the universal law of gravitation equal to the mass of an object times g, you can cancel out the masses of the objects, leaving you with an expression for g. The universal gravitation constant times the mass of the exoplanet over the radius of the exoplanet squared. From there, we can substitute in the values which we got from our earlier experiments and configure that g equals 7.048, which is a little less than that of the Earth. To conclude, let's look at the habitability of Kepler 70b. It is completely uninhabitable, mainly due to its extremely high temperatures that erase any chance of having liquid water. Even further so, the red giant phase of Kepler 70 eliminated this planet's atmosphere and almost any chance of finding life. Here are my sources, and thank you.